Here we go, guys. It is Tuesday, October 27th, 2020. We're going to be looking at normal distributions slash curves, kind of more formally defining those, drawing normal curves, and the 68, 95, 99.7 rule. Some of you may have already seen these if you read ahead in the text, or if you try to do the last problem on last week's quiz, where I had not figured out where we were going to end. So here we go. We're going to look at these things. If you are taking notes, please have those ready. We're going to have some notes today. Here we are. All right, so the normal distribution. We jumped into this a little bit last week. Right, in the normal distribution, the mean, that little Greek letter looks kind of like a U, but also kind of like an M. That's, this little guy is mu. Kind of like a little kitten. It says mu. And the standard deviation, sigma, completely determine the shape of a normal curve. All right, so if I have those two pieces of information, I can draw the curve. Mu can easily be seen as the center of the peak of the curve. Sigma, or the distance from the center of one standard deviation, can be seen in the curve as the points at which the change of curvature on a normal curve takes place. We're not going to have to calculate when that takes place. Those types of calculations take place in calculus, which we're not going to do and we're not going to worry about. It's just a way of kind of looking at a curve, a normal curve, and identifying where those distributions could be visually. These things are only true for normal distributions. Oopsie daisy. Didn't mean to do that. So this is again kind of our setup here for the formal definition of a normal distribution. Okay. Can you raise your hand if you need more time to write any of this down? All right, looks good. All right, so here's our formal definition about the normal distribution and normal curve from the text. A normal distribution is described by a normal density curve. Any particular normal distribution is completely specified by two numbers, its mean, mu, and standard deviation, sigma. The mean of a normal distribution is at the center of the symmetric normal curve. Standard deviation is the distance from the center to the change of curvature points on either side. We abbreviate the normal distribution with mean, mu, and standard deviation, sigma, as n parentheses mu comma sigma parentheses. Right. Most of what this definition says we had on the previous slide. The big new thing is our new notation here that tells us how to like abbreviate normal distribution. That's this part here. Right. The n, meaning normal, parentheses, mu comma sigma. That notation tells us we're dealing with a normal distribution with a normal curve with a mu and sigma that are already given. With those pieces of information, we can draw that curve. All right, so why? Why is this normal distribution important? Well, I'll tell you. They're good descriptors for some distributions of real data. Isn't that convenient? Such as scores on tests taken by many people, like the SAT or IQ tests, right? When we compile all that data, we usually will get something that is a very well described by a normal distribution or a normal curve. Okay. It can also model repeated careful measurements of the same quantity. Okay, so when we repeatedly do the same thing over and over again, like taking measurements. In this case, they're using the diameter of a tennis ball. If we're having a factory that's producing tennis balls and we're constantly like taking the same measurement of all these balls, there's going to be a small variance from ball to ball. And if we compile all this data, right, it'll fall into something that could be very closely approximated by a normal curve. Jocelyn, yes, absolutely. Go take care of your business. All right. Then characteristics of biological populations, such as lengths of crickets or yields of corn. Bye, Jocelyn. You too. Have a great day. All right. Again, these types of things that we have many, many measurements for, and there's kind of like a normal variance, like a smallest and a largest and a bunch of stuff in between. Those will typically be able to be modeled with normal distributions. Again, they provide a good approximation of the results of many chance outcomes. Right? So if we were to flip a coin a number of times, the number of heads, right, if we were keeping track, so let's say we had all of you guys flip a coin 20 times, and you only counted how many times you got a head, right? The number of heads out of 20 tosses of a fair coin would most likely, if we compiled all this data, fall into a normal pattern or normal curve, right? Many statistical inference procedures are based on normal distributions, right? That's the other reason why they are useful. So these are some reasons why they become useful and why it's something that is studied in statistics, is because we can pull a lot of data from it and it models a lot of real life situations. Not everything. Not everything will be modeled by a normal distribution. But there's a lot of things that will. Okay. Can you raise your hand if you need a moment to write anything from this screen? So now, we're going to go over the steps of drawing a normal curve. There's a nice little process we can use that will work on most normal curves. I won't say it's 100% perfect, but it is pretty darn good. All right, so step one will be draw a number line with 7 evenly spaced tick marks. Label the 1 in the middle with the value of mu, and those to each side with mu plus or minus sigma, mu plus or minus 2 sigma, and mu plus or minus 3 sigma. We're going to do an example of drawing this shortly. So if you're not entirely sure what all this notation means, the example will help. Then you will draw a dot above the mean value where the peak of the curve will be. Above the marks, 1 standard deviation from the mean, draw dots about 60% as high as the dot above the mean. So a little more than halfway, right? Above the marks 2 standard deviations from the mean, draw dots about 15% as high as the dot above the mean, or about 1/4 as high as the dots above 1 standard deviation. It's probably going to be a little easier to associate it to the standard deviation it's closest to, so, but that's up to you. Above the marks 3 standard deviations from the mean, draw dots just above the horizontal axis. Okay, so the last dots are just kind of like just barely up there. And then finally, you will connect the 7 dots with a smooth curve. All right. So these are our steps. Seems like a lot. It's not too bad though once you do it. So that we can draw a normal curve. All right. Can you raise your hand if you're writing down these steps and need more time? Right. Let us pause. All right. So we're gonna try and draw one of these. Hopefully it cooperates with me this morning. Let's just hope. All right, so we'll have a line. And we're gonna try and have as equal spacing as I can manage. Seems reasonable. All right. And so then we'll have this middle point of our 7 points. This will, right? This next one is mu plus sigma. This is mu plus 2 sigma. Mu plus 3 sigma. Right? And the other side, we're subtracting the standard deviations. So to the left, we have mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. Right? So that's where we get the plus or minus. It's just a way of notating that I'm doing both operations. Just one's happening to the right-hand side of mu, one's happening to the left-hand side of mu. Now, we make dots. All right. Now, this is just a general example. Like this would be based off of, just a normal distribution with mu as the mean and sigma as standard deviation. We don't know what those are. This is just showing how we would use those. All right, so I'm going to put my top of the curve up here, above mu. Right, and so then right here, right, this is essentially the middle. If I can draw a straight line, it helps, but you get the idea. Right. Now, one standard deviation away to the right, I'm going to go a little more than halfway up. Right, I'm at 60%, and then I'm just going to go directly across and do the same thing. One less. Then 2 standard deviations away. I'm going to go about, let's say about 15% of the way up from compared to the mean, or a quarter of the way for the 1 standard deviation. So I'm going to look at like halfway would be about there. So I'm going to go another half. It's going to be somewhere around here. Go directly across, mark that up again. It seems a little high. Good. All right, and then on our last one, it doesn't give us like a percentage of height compared to the other things. It's just like, okay, now put a dot like we're right down here at the bottom. Should be just a little higher than your line, your horizontal axis. All right, so here's our dots for our curve. Now, let's see, let's make our curve that color. So now we need to draw the curve, and we just want to kind of, as best as we can, draw a smooth curve up through our line, up through our dots. As you can see, I'm not very good at it. And it's just going to kind of flat line out. Should not bounce up. No, that's the best I can do. All right, so as you can see, it ain't going to be perfect, but it's going to be close. Wow, yeah, I should just stop while I'm ahead here. However, that's the process. All right. And so we can consider these points here, the inflection points, all right, or the change in the curve points. I forget exactly what we said earlier. All right, so how curved or how sloped downward our line is changes at these points. Right? That's kind of the idea. So that's our normal curve. What questions do you guys have? Okay. Do we need another moment to draw this if you're putting this in your notes? So that brings us to our 68, 95, 99.7 rule. All right, last week, we saw the distribution of ITBS vocabulary scores is symmetric, single-peaked, and bell-shaped. And if you don't remember that, the graph is here, and that's okay. Suppose the distribution of scores is exactly normal with mean mu equals 6.84. See that here in the middle. And standard deviation sigma equals 1.55. The figure to the right shows the normal density curve for the distribution with the points 1, 2, and 3 standard deviations from the mean. All right, and I've got these labeled here for us. All right, we can see one standard deviation to the left puts us at this 5.29. One standard deviation added to the right gets us 8.39. When we go to 2 over, we're up to 9.94 on the right, subtracted to 3.74. And again, if we mark these points on our curve, these are the points at which the amount the curve is like declining changes the most, essentially. All right. And so we have 1, 2, and 3 standard deviations to the left and to the right. Okay. So this is just another example. On this screen, we have our drawing of the curve. We have our standard deviations labeled. Yeah, this is kind of based on what we saw last week. All right. So this gets us to 68, 95, 99.7. Why do we care about where 1, 2, and 3 standard deviations are away from the mean? Because it tells us lots of information. That's why. This is our 68, 95, 99.7 rule. In a normal distribution with mean, mu, and standard deviation sigma, approximately 68% of the observations fall within sigma of the mean. That means within one standard deviation, so one to the right and one to the left. Right, so the middle section that is within one standard deviation here represents approximately 68% of the data in any normal distribution. We get approximately 95% of the observations fall within 2 sigma of the mean mu, or 2 standard deviations. So from -2 here to +2 here, this area under the curve is 95%, or approximately 95% of the data. Approximately 99.7% of the observations fall within 3 sigma of the mean. So again, we have -3 here, +3 here. 99.7% of our data is under the curve between 3 standard deviations of the mean. So we're only left with that like 0.15 over here, 0.15 on the left side, as far as the remaining bits of data, right? Okay. And this definition in the graphic kind of has the definition in it, right? So the graphic can be very useful. And we'll kind of see how to use this with an example here next. And we'll get a better idea of how to use this information. Can you raise your hand if you need more time to write or draw anything from this screen? So here we go. We're looking at our same ITBS score graph. We've got our standard deviations kind of marked along the top, and the actual numbers that correlate to those standard deviations or correspond to those standard deviations along the bottom here. We're going to use this to answer some questions. And we're also given our notation N 6.84, 1.55. So again, the first number in this notation is mu, it's our mean. And the second number is the standard deviation sigma. Okay, so that means that this right here represents 1.55 units, whatever the score is, whatever unit that is. All right, so what percent of the ITBS vocab scores are less than 3.74? All right, so that means we need I need to know what is the area under the curve, right, to the left of 3.74. Make that last a little bit too. Right, what is this area under the curve? All right, and so we know, right, based on what we know, I know that from here to here is 95%, right? So that leaves another 5% left over. So this portion over here is part of that 5%. But the way that this is set up, it needs to be, that 5% has to be evenly split between the less than 3.74 and the greater than 9.94, or like 9.94 and greater. Right? The way these work is similar to like percentiles, right? So between what's on the right side of the 95 and the left side of the 95, they equally share the 5%. So that means this area, right, less than 3.74 represents half of 5%, or 2.5% of my data. Okay, since I know that between two standard deviations is 95%, then half of that 5% that's left over goes to the to the left side, the other half goes to the right side. So we have what's the percent? 2.5% of ITPS scores are less than 3.74. Okay, excellent. So now they want to know what percentage of the scores are between 5.29 and 9.94. All right, so let's look at this. Let's look at what area they're talking about here. All right, so we are between 5.29 and 9.94, so I'm basically looking at this whole space here. It's going to take longer than I want to highlight all of it perfectly. Right, so this is where we're looking at, 5.29 to 9.94. So again, we look at what do we know. Right, I know what that color. That from the 5.29 to 8.39, that is my 68%. All right, and now I need to add in what percent is from here to here. All right. So again, I know that from here all the way over is 95%. So I need to find out what the difference is between 68 and 95 and then take half of that because I only have 1/2 of that other added portion of standard deviation. All right, so we'll do the math. And we have 95% minus 68% divided by 2. Right, because I don't have both of these sections. Right? I don't have between 1 and 2 and between 1 and 2 on both sides. I just have between 1 and 2 standard deviations on the right-hand side. So I want the percentage of that added to the 68% that's included in the portion I'm looking at. So that will give me, let's see, 30, 20. Oh, man. $27 divided by 2, 13.5, 13.5 plus 68. If my mental math is anywhere correct today, I think that's 81.5. I don't know why I'm trying to do it all in my head when I have a calculator. Yep. It is 81.5. Right, and that's because this portion here, again, was 13.5%. If we wanted to, we could create a labeled graph that tells me the percentage between each deviation, right? We could build this up. We have 13.5, 2.5, 2.5, right? From here over is that other 0.15, 0.15. We get these little bits and pieces. I'm sorry, 2.5 is all the way over. This is between here and here is a little less than 2.5. Sorry. That's from 2.5 over. Sorry, I'm gonna erase this. Oops. All right. So again, that's how we can use this information. And again, we'd want to write out our answer as a sentence and not just say 81.5%. So finish that to be correct. 81.5% of scores are between 5.29 and 9.9. Oy vey. That did not write for me. 9.94. Period. All right. Most stupendous. What questions do you have? Good. Okay. All right, does anyone need another moment to write anything down from this slide? Okay. All right, that is the end of our presentation. So I'm going to end the slideshow. Yes, I want to keep those. And I'm going to go. All right. Here is our weekly module. We have our week 10. Again, we're still in section 2.2. We'll be in section 2.2 on Thursday as well, about density curves and normal distributions. I will get our notes and the recording posted into the live class resources later today. There are some videos dealing with the normal distribution that are in here from AP Daily. The section here is all of 2.2 that we've covered up to this point. So it starts at the beginning of 2.2 and page 112 is kind of where we ended today. And again, we have our digital textbook here if you'd like to use it. And then, here we go. The discussion board is about the 68, 95, 99.7 rule. All right. You're going to have to sketch the normal curve using the normal definition here with a mean of 64.5, a standard deviation of 2.5. Label the points 1, 2, and 3 standard deviations from the mean. All right. And then answer these questions very similar to what we did in the example today. And then there's a discussion board for Thursday that I have not opened yet because we haven't talked about what you need to do that one yet. I might release it later today or tomorrow. And I'm still putting together the CYU. I have to decide what I want to do for that. Okay.